Okay, yeah. Um, yeah, I want to talk about some approaches for hardware-independent accelerated X drivers. Yeah, let's start with the current situation. So, uh, where are we today? We have a lot of device-dependent X drivers for graphics stuff. If you go around, you can find drivers for pretty much every device out there. But if you look closely, only a very small subset of them really provides some modern acceleration. So modern acceleration in the sense that it actually works with a modern X server, which is pretty much EXA today. And yeah, even a smaller subset provides good EXA support with really some good acceleration and is well maintained. And this basically comes down to only 3 drivers, which are the Intel, the Radeon, and the Nouveau drivers, which are providing good support. Yeah. So, yeah, drivers that don't get maintained well even get features removed, so or acceleration features removed. So we've recently cut out this XAA acceleration from the X server, so pretty much all those old drivers that had some sort of acceleration don't work anymore. They just do CPU rendering. Yeah, it's not really what we want. Yeah, also it's hard to provide a good acceleration support. The X-render protocol together with the X-composition extension is just a really feature-rich protocol, so implementing every operation that's in there is basically impossible for the communities we have today. So most drivers just bail out and just implement the most used operations in rendering paths today. But the problem is, yeah, we have different implementations. So what Radeon implements as most used operations is different set from Nouveau, for example. So there are different levels of acceleration, and even the notion of most used operations can shift over time. The most notably things are when libraries that are used by many applications to render things like Cairo are changing. You see a huge difference in used paths or operations in the rendering. So yeah, just stating the obvious, we have a huge problem with developer manpower in the export. So yeah, we're pretty much doing minimal effort in the DDX drivers to provide the users with what they actually want. So recently, or in the past, there were some attempts at unifying all this with generic acceleration architectures. So this 3 just implement the EXA acceleration, and yeah, this 3 Glamour, which is using OpenGL as a backend for doing all this stuff. The Xorg state tracker, which is using Gallium as a middle layer to get an hardware-independent layer of doing all those operations, and more recently the XA state tracker for X acceleration, which is also using Gallium but is not quite a complete X driver. It's just like Glamour, it's a backend you can plug into any X driver to do the acceleration work. So yeah, I've done some benchmarks to provide you some insights on the performance implications of those different approaches to do generic acceleration, and to actually define what this acceleration is we're talking about here. You'll see it's not quite what you would expect from the word acceleration. Yeah, I've carried out the benchmarks on an AMD Fusion system because it was the easiest way to get all those different acceleration architectures running, and yeah, it provides some good balance between CPU and GPU performance. Yeah, for example, I've run some of these tests on my machine at home, and with a strong CPU, you won't notice when you get fallbacks or stuff. So the CPU just is a lot faster than the GPU, so you won't notice anything. Yeah. Yeah, I've equipped this machine with a large amount of RAM to make sure that's not the bottleneck, and it's pretty fast run, so the fastest you can put into this machine. Yeah, so software used for this benchmarks, the Fedora 17 in a stock configuration just updated all the libraries that are related to the tests I carried out. So libdrm, Pixman, Mesa, the Radeon driver, and Clamor are all from Git as of last week. So you're really getting the latest and greatest. Yeah, for benchmarking, I used the Cairo path trace, which is sort of a gold standard to do X acceleration benchmarks. Obviously, I used the benchmark subset of the Cairo traces, which you can find on the free desktop Git repository. This consists of 25 traces stressing different rendering paths from the different drivers. So, yeah, what I actually did is comparing all those different acceleration architectures against pure CPU rendering. So the different tests carried out were pure CPU rendering, obviously, to get baseline with the image backend of Cairo, which is just using Pixman to render everything on the CPU. Acceleration on bare hardware, so the Radeon driver with its handwritten shaders for the Radeon hardware. The Glamour backend in the Radeon driver to do all the things over OpenGL, and the Xorg state tracker because it was the easy way out from the state trackers. The XA state tracker would require more work because it's not a complete DDX driver. So, yeah, results from this benchmark. I won't show you all those bars. If you want nice looking bars, go over to Phoronix and look at those. I'll just tell you some facts about this benchmark. So, yeah, the image backend from Cairo and the Radeon driver running on bare hardware are able to run all 25 tests from the test suite without any failure. Clamor fails to run one of those tests with a kernel panic. And the baddest is the Xorg state tracker, which fails 3 of those tests, also with a kernel panic, and also it has some huge problems with scanout. I think this is related to the late addition of 2D color tiling in Mesa in the kernel. So the image you see on the screen are pretty much messed up, but you still can run the test from another virtual terminal. So it works sort of, but not quite. On Nuvo it's much better. Yeah. The pretty much most important result from the acceleration point of view is only 3 or 4 tests out of these whole 25 tests are actually faster when rendering on the GPU than just doing CPU rendering. So, yeah, and that are also the tests where a lot of stuff is going on the screen. So pretty much the Firefox tests with all those HTML5 stuff where you pretty much run into a fill rate limit on the CPU, and that's really where your GPU can shine. So those are a lot faster in GPU rendering. yeah, that's not a result of this benchmark, but yeah, the only DDX driver that can compete with CPU rendering is the Intel driver with Sandy Bridge new acceleration. Yeah, that's not in those benchmarks, but you can go over to Chris Wilson's blog and just look at all those nice graphs. So you see it's actually comparable in speed to the CPU rendering in pretty much all of those tests. Yeah, results. Glamour provides the most consistent experience, so it's not too fast in any test or phase to run any test or be slow in any test. So yeah, it's compared to the other drivers, it's still slow. In its best case, you get pretty much 25% faster rendering on the GPU with Glamour than doing this on the CPU. And keep in mind, those are the Firefox tests where your GPU is really better suited for. But also, the slowest tests are 8 times slower than CPU rendering, which is not bad compared to the other drivers. Yeah, the Radeon driver on bare hardware gives you pretty much good best case speed. So in those Firefox tests, you get 3 times more performance than doing it on the CPU. Yeah, there's one bad exception where you get 20 times slower rendering than doing it on the CPU. But most of those tests are around 2 times slower than doing it on the CPU, which is not bad. Yeah, the Xorg state tracker is not that far away from the Radeon driver. It even has one test where it's even faster. So you can say the shaders that are in the Xorg state tracker are actually better for this kind of acceleration, the one test exercises, than the ones that are handwritten on a Radeon driver. It's also the test with the most overall wins, so it's the only driver that is in 4 of those tests faster than CPU rendering, where the other 2 tests are just there are just 3 tests where it's faster. But yeah, keep in mind it's also the driver with the most overall fails. So yeah, from a user experience, kernel panics and those graphics benchmarks are not a nice thing. There are also 2 bad exceptions with 10 times slower than CPU rendering. So after I've flashed all your minds with all those benchmarks, don't get fooled by the speed benchmarks. Speed benchmarks are important to know where we stand, but they're not the only thing that matters from a user experience kind of thing. What users want is a responsive system. You won't go around and update your Radeon driver and say, oh yes, I've got a 10% speed increase in this operation, unless you're named Michael Arabella and running for Onyx. But yeah, as a user, you want your system to be responsive, and acceleration, even if it's not faster than the CPU only rendering, it contributes a lot to responsiveness and kind that it's doing offloading. So your CPU is actually free to do useful things in the applications you're running, rather than it's just rendering your user interface. So we really want to have acceleration of some kind, even if it's not faster than CPU rendering. Yeah, as the talk was mentioned with a discussion part, I want to show some ups and downs of the different architectures. We have Glamour, which is in a fairly good state because it's actively developed by Intel guys, and it already supports a rather large amount of operations compared to the other drivers, and they really put a lot of effort into it. But yeah, the downside is it's still slow. Even there's going a lot of effort in optimizing lately. It's the slow, and in my opinion, this is partly because those 2D operations we are doing does not fit well within OpenGL. OpenGL has just a really large overhead setting up all those states and things, and yeah, we can do a lot better with a thinner layer between the GPU and the user that wants some acceleration. Now, the Xorg state tracker, it obviously provides fairly good performance as shown by the benchmark, but yeah, that's kind of the only nice thing to say about it. It has kind of an ugly code base. You don't want to really work with that. It still has many fallbacks where stuff is in there but deactivated because it's not really well tested, and they're still missing a lot of things, but yeah, it's not actively developed. There wasn't any activity in recent days, so I've kind of played around a bit with it and did some things there, but not much, and I don't really want to work on this. Yeah, the X acceleration state tracker. Yeah, the nice thing is it's mostly a copy of the Xorg state tracker in kinds of acceleration code. So it should be as fast as Xorg state tracker because yeah, it's the same code. I say should be because I haven't tested it. So yeah, but it should. And it has a really nice cleaner code base. There are a lot of cleanups in there compared to the Xorg state tracker, and I could imagine really working with this code base going forward. So the problem is there's also node development in ages, so it pretty much got pulled into the Mesa tree after the VMware guys released it, and since then there was not really much development going on there. Also, yeah, it needs some front-end driver to really do something useful for the users. So you could use it as a backend for like Glamour for the existing DDX drivers, or you could go to a way that the Xorg state tracker tried to do and do a one-size-fits-all driver for all the hardware which has some kind of gallium interface. So yeah, I think it would be a really nice thing to have a unified driver for all those things, especially as from the user perspective. It would be really nice if you swapped around your cards from NVIDIA to AMD or the other way around and don't have to fiddle with all those configuration options which are different between those two drivers. So yeah, that might be a thing we can talk about. So yeah, I'm already at the end of my presentation, so I'm really open to your comments, questions, anything. So pretty much for the Radeon guys. Could you imagine working with something based on the Gallium architecture rather than going with the Glamour thing you're doing right now?
Maybe first? Well, just, is that okay if I start here and then...
Yeah, I could definitely imagine that. I mean, I think, as you said, I think our biggest problem is lack of manpower.
Yeah.
So whichever solution attracts the most manpower and allows us to get the most out for all the drivers, I think is the solution we should choose. And we are definitely not, you know, for us it's not, we want to do Glamour and nothing else. It's just that I just wanted to implement Glamour support in the Radeon driver so we can evaluate its performance and
Okay.
see where it goes.
Yeah.
The good thing about the really good thing about Glamour is that it's still actively developed. So when you have some kind of problem or crash or something that's not accelerated, you got somebody to ask. If I have a problem with the Xorg or XA state tracker, it's not so easy to get somebody involved with your problem and help you to fix it.
Okay, yeah. Valid point. So, but yeah, we've also seen this development recently where Radeon and also Nuvo are gaining 3D support in Gallium a lot faster than the 2D support in the DDX. And yeah, so it would be really nice to really reuse this on this level.
I just got a question related to the benchmarks you quoted. You already said that the purpose of acceleration is more offloading onto the GPU than actual speed. With the benchmarks you quoted, is there any weighing of how much that actually matters? Because you mentioned before that the 4 tests that were better were the ones where there's lots of stuff happening on the screen. So what I'd be interested in as a user who doesn't actually know too much about acceleration is like, is this a use case I actually see every day, or is that something that's just a benchmark? So if a benchmark gives me 100 numbers, which 10 do I actually have to pay attention to?
I think it's more a thing where when you really fail in one of those benchmarks, you'll notice as a user. Yeah. So those benchmarks vary 10 to 20 times slower on the GPU than rendering it on the CPU. You really get into trouble because you'll notice it as a user. And especially all those Firefox benchmarks, there's so much going on the screen, so you basically need those acceleration. And yeah, it kind of works today, so you see this speed up in the acceleration there. So,
yeah. For 2D applications, there's really only one number you care about, that's text drawing. Nothing else matters. It's nice to be able to do scrolling with accelerated blitz, but applications just don't paint much geometry to the screen other than rectangles. And so essentially any acceleration architecture that makes text go faster without killing your scrolling performance is a good one. We spent a lot of time accelerating geometric operations to make the Mozilla HTML5 benchmarks go faster. But look at your desktop. Is there a single polygon on your screen which is not a rectangle? No. So the reality is that for the 2D environment, as long as we can make text go fast, and text is really hard, then everything else is just in the noise.
So looking at the results you had, the places where Glamour was doing well was in these sort of HTML5 demos where it's mostly big scaling operations. And sort of the flip side is where you're losing right now is text. The problem that I see with text right now is that we're going through this component alpha rendering pass where you make a temporary mask, you add your glyphs into the mask, and then you do 2 separate composite operations into your destination to represent the 2 source alpha values that you have in the component alpha render operation. Glamour has some tricks to avoid the mask in some cases, which is kind of magic looking. I haven't actually reviewed the code, but apparently it works. So the remaining problem is that we're still doing 2 separate state changes onto the destination. The good news is that in current Mesa, GL 3 point something, but it's an extension we have exposed, there's our blend func extended that lets us actually get 2 blending values out of the fragment shader. With that, we should be able to avoid the state changes in each span of text, which should massively cut down our CPU overhead for text. It might make GPU text actually competitive with CPU.
Might. Yeah, but then we also have those functions exposed long ago in the Gallium interface, so it's just, OpenGL now gaining the support for this kind of stuff, and if we had actually some development on those state trackers, we could have done this long ago with the current gallium interface. They support for this for a long time now. Also in the drivers like Nuvo.
So Keith, I'm a little confused, and you can help me here. So as we move more and more to apps that are rendering using SVG and then HTML5, which definitely is the trend. So far I think a lot of the SVG has been rendered offline and then dumped as pix maps onto the screen. Is that going to change? Is that going to impact sort of what matters in terms of acceleration architecture, those two things?
I think the bulk of application rendering going forward is going to move from a core protocol and render extension based acceleration to pure GL, as GL gains the capabilities like the ARB extension for component alpha rendering. As we get those capabilities into the GL stack, as we get things like decent anti-aliasing into the GL stack, we're going to be able to use GL for all of our application rendering, and we can get rid of this dependence on the legacy core 2D acceleration operations. There's still a couple of things which are necessary in the core. In particular, if you're not running a composited desktop, or even if you are and you want to do scrolling, we still need to be able to do 2D blitz. But the actual construction of application content is moving away from these APIs. And as long as we can run existing applications efficiently through the core protocol, we'll be able to retain our existing 2D. And right now, you can't run these applications over the net because the bandwidth they consume in the X protocol is so high. They're not fun to run over the net. But applications that existing applications that run well over the net, like GitK, which is the only thing I run over the net on a regular basis, those, as long as we accelerate the operations that the existing 2D applications use efficiently in our existing core protocol, and new applications start using OpenGL and OpenGLES for all of their rendering as OpenGL becomes more competent at doing 2D graphics. I hate to see us spend a huge amount of time worrying about 2D graphics, especially about geometry in the 2D environment, when these applications can use an API which is directly designed to drive the hardware that we have on our machines, like OpenGL. I get really unexcited about doing any 2D architecture other than making text go really fast, because that's all that matters for applications that can run effectively over the wire today. And everything else should just be using GL anyhow, because that's what the hardware does. We have GL hardware. We don't have X hardware. So if you're not using the GL API to drive your GL hardware, it's either because GL doesn't support the operations you want, and for text it looks like we're getting there, or because you're trying to use the existing X2D protocol. And we need to make and applications that are using that are applications that are designed to paint rectangles of text on the screen and not paint geometry. The render protocol does a terrible job at exposing geometry. It's very poor acceleration, very poor formatting for it doesn't support vertex buffers and all of the modern ways that you get acceleration, efficient 2D acceleration. And so, I mean, even the modern 2D acceleration architectures, an NVIDIA extension is coming out that does really nice 2D acceleration, but it's all dependent upon having the state loaded into the hardware and manipulating the state in the hardware, not transmitting information. And all of our existing X APIs are all immediate mode only. And that it doesn't, immediate mode is not what the hardware does. X acceleration, the X primitives are not what the hardware does. And applications are moving away from immediate mode rendering and 2D only operations and blah, blah, blah. So we need to stop worrying about the X acceleration that we have today, make what applications are using today efficient, and make sure that applications have a nice migration path to GL by fixing GL and by fixing our GL drivers. The problem is that most of the drivers that are interesting today to get X acceleration working efficiently and all the things we dropped XAA support that affected, we don't have GL for those. So any GL-based architecture is not very interesting because the chips that we need 2D acceleration for don't have a GL driver. So we need some way of supporting those chips. XAA was totally inappropriate for those because it couldn't accelerate any composited environment. So if you're running Unity, if you're running GNOME 3, if you're running KDE, XAA is not useful at all. You might as well go back to software rendering, which is what we've done. And that provides a better experience for the users. If we could provide competent 2D acceleration for those chips that just accelerated Blitz and painting solid rectangles, those chips would be in pretty good shape, much better than they were with XAA. But depending upon a GL environment just doesn't make any sense, because if you can have a GL driver, you're just going to run GL applications.
But the point I'm trying to make is GL is pretty much the high overhead path to the hardware, at least for us. You can really do better if you're closer to the hardware, and Gallium is this interface which is really closer to the hardware. So if we have something that is more appropriate to plug in as a backend for example, Cairo or something, it really will make a difference.
GL is high overhead on Gallium because Gallium. No, because Gallium introduces a lot of overhead and everything to everything middle layer that doesn't match the APIs and doesn't match the hardware. So that overhead that you're seeing is not GL, right? If you try to run
it's pretty much
on GL drivers, it's a very different experience, and that's why all the GL benchmarks on Gallium drivers kind of suck.
Oh no, I don't think so. Yeah, but we are also changing the Gallium interface and to match hardware, and especially in the embedded space, we have still hardware where you have dedicated 2D engines and stuff which you could eventually expose through the Gallium interface and use it as a means to accelerate something, which you cannot do with OpenGL. It just doesn't fit well within this. Okay.
Okay, well, seem to be no more comments, so thank you, Lucas. So